Before we start this video, I just wanted to say that this video isn't solely about electrons or atoms. It's about curiosity. What we're looking for is why do things work the way they do. Quantum physics may seem abstract in the beginning, but once you understand it more and peel it down layer by layer, it becomes more simpler, and you will have a greater appreciation for it. But similarly, just like how electrons absorb and release energy in the form of light, you too can take your energy and release it into something meaningful, your passion. Elements on the periodic table are composed of atoms, the most basic building blocks of matter. Chemistry, in fact, is the study of matter and the changes matter undergoes. All atoms build substances such as gases in the air, even to the cells of your body. And when we talk about atoms, we're talking about three subatomic particles: the proton, the neutron, and the electron. Protons and neutrons reside in the middle of the nucleus of the atom, and protons, they have a positive charge, while neutrons have a neutral charge. And when we talk about electrons, we're dealing with something completely deeper and different, known as quantum physics. And electrons, they have a negative charge and reside in something that's called orbitals outside of the nucleus. Much of chemistry can be explained by its parent science, physics, which deals with energy and motion. And when we talk about energy and electrons, we deal with energy in many different ways. Electrons exist in different energy levels, the lowest of which is n equals 1, which is known as the ground state. Each energy level is like a different step known as quantization. Quantization means electrons can't leave or change their energy level unless they absorb or release energy. But before we talk about that absorption or release of energy, we need to talk about why the four quantum numbers define an electron's behavior. The first of which is the principal quantum number n, which defines the electron's energy level. The second is the angular momentum quantum number L, which defines the shape of the electron. The third is the magnetic quantum number m sub L, which tells us the direction of the electron around the nucleus. And the fourth is the electron spin, the spin of the electron, either up or down. Together, these four electrons help us understand where an electron exists and how it behaves. But, we can't exactly know where an electron is and how fast it's going at the same time. This is known as the Heisenberg uncertainty principle. Imagine a bee flying somewhere in a room. It's buzzing around, doing whatever it does. Quantum mechanics basically tells us the size, the shape, and the orientation of that room. Quantum mechanics also tells us the structure of the electron's world, while the uncertainty principle limits ourselves on how precisely we can understand that world. And together, the two of them help us understand matter on the tiniest scale. Electrons behave like a rock that is pushed up a hill. A rock requires an absorption of energy in order to get to the top. And once it gets to the top, the rock naturally releases that energy, going back to the ground. Similarly, electrons tend to be in the ground state, closer to the nucleus. This is because opposite forces attract each other, right? The negatively charged electrons naturally attract themselves to the positively charged protons in the nucleus. So what does this mean? The excited state doesn't last very long for the electrons. In the excited state, the electrons release energy in the form of light, known as photons. Photons are tiny packets of energy, and once those photons build up, they create something that's called an atomic spectrum, which is a set of colored lines that is unique to each element. Do you ever wonder why neon signs glow? Well, those are just excited electrons releasing energy in the form of light. Once emitted, an atomic spectrum of light is seen in the form of wavelengths, each with a different frequency and vibration. Frequency, in terms of waves, tell us how many waves pass by per second. So if a photon has a high enough frequency, that means it's vibrating really fast with high enough energy. This is why we identify elements using the study of spectroscopy, the study of the frequency of light. For example, the color violet has more energy compared to red because its waves vibrate faster and their photons contain more energy. In 1801, Thomas Young's double-slit experiment proved that light could behave like a wave, creating interference patterns. Later on, scientists performed similar experiments using electrons, and they found out that electrons also have wave-like interference patterns, and that they proved that particles could also act like waves. In 1905, Albert Einstein described the photoelectric effect, saying that light behaves like a particle, and that light, photons, with a high enough frequency, to knock electrons off a metal plate. Both of these experiments enabled Louis du Bois to propose his wave-particle duality theorem in 1924, stating that electrons behave as both waves and particles. Energy, it's not continuous. It absorbs and releases energy in the form of photons, which is a single quantum of electromagnetic energy. You see, systems in nature tend to favor lower energy systems, like we explained earlier with the rock. But how is this possible? That totally contradicts classical physics. Well, imagine you toss a pebble across a lake, but you shrink that pebble to the size of an electron. Ladies and gentlemen, that's quantum physics at the heart of it all. Hard to imagine, but very interesting nonetheless. And just like electrons don't stay in one place, maybe we shouldn't either. If you're curious about something, go chase it. Whether it's science, music, art, or anything else, let your own curiosity pull you into your own excited state.